This talk is to introduce how to improve the submodular maximization problem with routing constraints. The authors are Pao-Te and Kuo-Shih from the National Central University. There are many robotic applications can be reformulated as submodular maximization problem. For example, in spatial search, the robot tries to cover the area within a path constraint. For example, in map exploration problems, the robot tries to maximize the environmental coverage within a path constraint. For example, in autonomous disinfection problem, the robot tries to maximize the disinfect surface within a path constraint. In locomotion problem, the four-leg robot tries to maximize the explore terrain within a path constraint. Those problems can be reformulated as the same mathematical form, which is maximize f of s subject to c of s smaller than or equal to b. In fact, this problem includes two NP-hard problems. The first one is maximal coverage problem, which is to find the k-maximal coverage set from n ground sets. The second one is traveling salesman problem, which is to find the minimal path from the k sets. So the first problem can be solved by greedy approach within theoretical guarantee if it has submodularity, which is about dimension return. The second problem can be solved by approximation algorithms. So far, the best lower bound of this problem is proposed by GCB. GCB is a greedy approach to maximize this problem. Its lower bound is more than a half of 1 minus 1 over e tight OPT. It's about 31% of tight OPT. Then the tight OPT is not optimal solution. It's a value smaller than the optimal solution. The tight OPT is relevant to some parameters, for example, submodular rate of the cost function, total curvature of the cost function, maximum number of select set, approximation rate of TSP algorithm. Then we can see this equation as the beta. Then the beta is smaller than 1, which means the robot cannot utilize all of the budget. Then our goal is try to improve this bound. So if we can make the beta as close to 1, then the theoretical bound is improved. There are two ways to do that. The first one is if the cost function is submodular, then alpha equals to 1. The second one, if the cost function is exactly estimated, the psi equals to 1. Finally, we will have a better lower bound than the GCB. In this research, we propose a submodular tree, which is a minimal spanning tree. The routing problem is solved by minimal spanning tree. By doing so, it has submodularity and is computable. Therefore, the alpha equals to 1, psi equals to 1. The other one is we find the sparsity of the tree. For example, this is the minimal spanning tree. Then we found that in spatial domain there are 2 to the 10 path cost values. But when we transfer it to the Fourier domain, there are only 21 Fourier coefficients, which is sparse in the Fourier domain. The experiments demonstrate that the proposed algorithm submodular tree outperforms other benchmark in coverage problems. In conclusion, first, the proposed approach submodular tree utilizes its submodularity to solve the submodular maximization problem with routing constraints. It gives us a half 1 minus 1 over e bar OPT guarantees, where it's better than the GCB. Second, the sparsity of the submodular tree is explored. Finally, the experiments show that the submodular tree approach outperforms other benchmarks. Thanks for your attention. If you have any question, please just send an email to me. Thank you.